Hello everyone, let's understand refraction of light by using wave theory, and in this case we'll consider a plane wavefront. A plane wavefront basically means that every point on the wavefront would be on a plane. To understand this, let's take a boundary called as P and Q as given here. So let this boundary be PQ. Let this medium be a medium with refractive index n1 and this a medium with refractive index n2. Let the speed of light here be v1 and speed here be v2. There are two laws of refraction. The first law is based more on observations which can't be proved here. So rather we need to prove the second law. So if the wave theory is able to explain the second law, then it means that even wave theory is a consistent or a true theory to some extent. The second law of refraction states that the ratio of sine of angle of incidence to sine of angle of refraction is a constant, and that constant, that is sine I by sine R, is equal to n2 by n1. So we need to prove this by using the wave theory or by using plane wave in this case. To understand this, let's look at the diagram given here. Let's consider a plane wavefront incident at an angle to the boundary AB. Let's call this as point A, this is point B. And let us call this point as A dash, and the corresponding point, that is the point on the same tangent, let us call as B dash. The point B dash is still in the medium 1 while the point B has hit the interface. Now it starts to refract here. The angle made at this point is called as angle of incidence I. Now every point on this acts like a secondary source. Every point here acts like secondary source producing disturbance. So these produce secondary wavelets like this. It's producing wavelets like this and like this. Similarly, this point has come somewhere here, so this will produce secondary wavelets. Similarly, this point. So by the time this point B dash comes to point C, the wavelets from the point C are gone somewhere here. Let us call this point as point D. So by the time the point B dash comes to point C, the wavelets or the energy or the wave has gone from point B to point D. So here, even this will start to produce its secondary wavelets. A common tangent drawn from here to this would be again parallel. So what we get is a plane wavefront, and what we get is again a plane wavefront. This is called as, this whole part here is called as incident wavefront, and this part is called as refracted. This part here is called as refracted wavefront. So this is the basic diagram. The angle made here, this angle is equal to R. It's not visible here. The angle made here is equal to R. We need to prove this relationship. To understand a better way, let's redraw this without drawing the common tangents. Let's look at a boundary. As seen earlier, let's call this as PQ, and on this is incident a plane wavefront like this. We call this as point A, this was called as point B, this was called as point A dash, and this was called as point B dash. Draw norm at this point. The angle made is angle of incidence I. So light refracts, assuming that the second medium is a denser medium. This is N1, this is N2, and then assuming second medium is a denser medium, light would refract. So the light would refract and go like this, the angle made here is called as R. This is the point B. Now, by the time the point B comes somewhere here, it comes to this point, say point C, the energy from here has come to point T, we saw earlier. So this is point D. So that common tangents, that is, if you draw wavelets, second wavelets for this, like this, and then wavelets from here, common tangent will be drawn like this. So just draw the common tangent. This is what is the common tangent. So light refracts here also, and light comes out like this. So this part here, this whole part would be the refracted wavefront. So we need to prove this Snell's law. Now the angle made here is 90 degrees because it's 90 degree here. It's 90 degrees. Similarly, the common tangent, so the angle made would be 90 degrees. It's normal to this wavefront. Now if this angle is I, then this also would be I only. To understand this, let's look at some basic geometry. Imagine that if the light ray falls like this, light ray falls normal to the surface, then this is point A, this is point B, this is point A dash, this is point B dash, this is surface B, this is the point Q. And this normal also, let's call this normal as N dash. In this case, N dash is also along AB only. So even N dash is along AB. Let's call this as N dash. So I in this case is 0. Suppose imagine that instead of falling along the normal, if it is inclined as seen here, then let us draw this. So and what we get would be something of this kind. This is what we get. So if this is point A, this is point B as it is, this is point A dash, this is point B dash. Let's look at this point alone. Now in this case, B dash, that is B dash, has moved away by an angle. This is the same angle by which AB has moved away from the normal. That is, the angle which AB moves away from the normal is same as the angle which B dash moves away from PQ. So if this angle is I, this also would be I. There's a theorem for it in mathematics. Let's not go so deep into it, just understand by common geometry. So the angle here also is I, as already seen. Suppose if the angle is R here, this angle here is 90 minus R, because N, that is N dash, is normal to surface PQ. This whole thing is 90 degrees, but this part is R, so this would be 90 minus R, and this would be R, because total angle in a triangle is equal to 180 degrees. So with this in mind, let's start the proof. Let's consider triangle, say B dash C. From this triangle, sine I is equal to, it will be B dash C by BC, and from triangle, say BDC, sine R is equal to, it will be BD by BC. So first let's find out what is B dash C and what is BD. If time taken for the energy of the light to go from point B to point C is D, and the speed here is V1, then B dash C would be speed into time, which will be V1 into T. In the same time interval, that is B dash C and BD are not same. That is distance from here to here and here is not same because they travel in different mediums, but time taken is same. That is by the time the point B dash comes to point C, the point B has come to point D. So even here, BD is equal to speed into time, which is t only, because we want to find the same time taken. So putting it back here, we get this as v1 into t by bc. This is equal to v2 into t by bc. Let's divide sine I by sine r. Then what we get is sine I by sine r is equal to v1 into t by bc by v2 into t by bc. From here bc gets cancelled and also t gets cancelled. Finally what remains here is sine I by sine r is equal to v1 by v2, but we want in terms of n1 and n2, so let's write v in terms of n. By definition of refractive index, n is given as c by v, or v is equal to n by c, rather c by n. Putting it back here, we can write this v1 as c by n1 and this is c by n2. From here c gets cancelled, therefore what we get from here is sine of I by sine of r is equal to n2 by n1. So this is the required law. So by proving this law, we have proved that refraction is explained by using wave theory. To understand that the point we are proving this thing is to make sure that even wave theory is a valid theory.